Okay, so we will learn this triangle centers. First notation for this, notion for this will be the congruence. So three lines, they are congruent. Not congruent, concurrent. I mean, just realized I said something incorrect. So concurrency, not a congruent, concurrent. They intersect. And this point is known as the point of concurrency. So if we have three lines, one, two, three. Okay, then this will be the point of concurrence. In general, they may be not concurrent. This is the general case. So being concurrent is a very special situation, very special. And not concurrent, this is the general case. Okay. The first application of this is the three angle bisectors. The three angle bisectors, they are concurrent. Okay. So if see, let me draw a triangle. label this A, B, C. We call this point I. Okay. In the following, I'm going to make a copy of this picture. See, make a copy of this. Doesn't work. Let me see how to copy this. Paste. Okay. Because of this, I'm going to remove the. I only need the center. Okay, the important thing about this is that if we mark these points E, F, G, we find that these three segments, they have the same size, same length. Okay, so we will call it the radius. We have a point, we have the radius, then we can draw a circle. This is the circle. Draw. Okay. Okay, now let's review the construction. How do we get this circle? First, we draw the three angle bisectors. We proved that they are concurrent. They intersect at a common point. Then from this common point, we draw three perpendicular lines. We denote the intersection point E, F, and G. Then we checked these three segments. They all have same length. Now we have a point, the point of concurrency, and the radius, you can draw the circle. It's easy to see the 3 points E, F, G are contained in on the circle. Easy part, the 3 points. Okay, it's because the distance equals the radius. Therefore, they are on the circle. But the not easy part, these 3 points at a tangent point. The 3 sides to the circle. Okay, let's try to recall how did we verify this. Not only they are on the circle, but they are also the tangent point of E is the tangent point of BC to the circle. F the tangent point of AC to the circle. G the tangent point of AB to the circle. Why are they the tangent points? Let's think about it. Jessica, let's turn on the camera. Okay, Jessica. Aaron, are you ready now? Okay, later. George and Peter.
Yeah, I'm back.
Okay, turn on the camera.
Okay.
Okay, let's see why. It must be tangent point. Amy, what's your answer to this? It's been a while. Maybe some theorem you have. By which theorem we can conclude they must be tangent?
I can speak.
Okay, George, you want to say something?
I forgot. It's like a sign like this. It means it's a 90-degree angle with the sign BA. It's a line in the circle that touches a line exterior to the circle. That's also like, I don't know, it makes 90 degrees. I don't know what you call it, but
okay. So let's check our previous lecture. Lecture 20.
I have my notes.
Okay, so this is from the last class. Last class we introduced, when we record the tangent line theorem. If it's a tangent line, then this must be perpendicular from last class. And also we learned the converse of the tangent line theorem. The converse is if this is perpendicular, then this line must be a tangent line. So we will apply this to our case here. Because so E is on the line, because it's perpendicular, this must be tangent. The perpendicular must be tangent. Okay, so the reason for this is the converse of our tangent line theorem. Because they are perpendicular, it must be tangent. Okay, not only that, we also learned how to find this length of the 6 shorter segments. AG, AF, BG, BE, CE, CF. Okay, so to find this, we call this X. We call this Y, because this is Z. And we have the length of the three sides. This A, this B.
Isn't this part where we explain like the Heron formula and stuff?
So we will combine this with the Heron formula. Okay. So the relationship is that we can see y, z, we add them, we get A. X, z, add them, get B. X, y, add them, get C. We have three equations.
Okay.
Okay. Three equations, three unknowns, x, y, z. How did we find this x, y, z? Anyone remember this from last time?
Forgot. I don't have my notes here.
Okay, Jessica, do you remember that one? No? Amy?
It was something like you did like y equals a minus c, and then like
Okay,
something like that.
okay, yes. So the point is, if we can, so later you will learn about the symmetry. So there's some symmetry of this system. If we add all three together, we have x, 2x, y and y, 2y, z and z, 2z. So the important step, the summation of the left-hand side equals summation of the right-hand side. And this is twice of our half perimeter. So from here, we conclude is our half perimeter. Then we see x will be s minus y plus z is our A. Similarly, y is s minus plus z. Then we looked up x plus z b. And z x plus y is c. Okay. This is how to find these values. But how do we remember this? To help you remember it, so this 2x is s minus a. So it's the half perimeter subtract the opposite side. We have a here, so this 2 will be s minus a. We have b here, so this 2 will be s minus b. We have c here, so this 2 will be s minus c. So how to remember the formulas? Because for x, it's the half perimeter subtract the opposite side. For those two, next to b is s subtract the opposite side. This will be s subtract the opposite side. That's how we remember the formula. Okay, we also used this to find the inradius. Let me make a copy of the graph. and remove the not needed term. Let me remove this.
Holy shit.
So for this part, I'm going to connect. Okay, so we will use the formula for the area of the triangles. We start with area triangle BIC. With half of base time the height. But this one, base is A. Height is the inradius R. Similarly, area AIC. Okay, let's try. Amy, give me the formula for the area of this triangle.
You can just do the base times height over 2.
For this one, the base will be AC, which is B. Height, radius. Area AIB. Jessica, what about this triangle? What's the area?
Half of C times R.
Okay, so it will be again half of base radius. Now if we add these 3 together, we get an area of ABC. So area ABC will be the summation of this. Okay, common factor R, 1/2 A, B, C, R. And this is the half perimeter R. And by the Heron's formula, we know that this is also combine the two, we get the formula for the radius. Area. It's the same as we can simplify this a little bit, not much. We can put this 1 over s under the square root. Under the square root, so s becomes s squared. We cancel one of them. Okay, so that's the radius. Okay, let's try some examples. First one, consider a special case. A 3, B 4, C equals 5. Do this number sound familiar? Jessica, Amy, do this sound familiar? Okay.
Like a squared plus b squared equals c squared 1.
Okay, so this gives us a right triangle.
Yeah, basically.
With 3, 4, 5. Okay. Samuel, what's the area of this triangle?
Area, we just
Mhm.
use the formula we used before, right? We plug in
Uh,
S.
Okay, we will do that later. Do you have other method to find the area?
Well, don't we just do like height times base divided by 2?
Yes. Okay, the easy one. The easy one. So area.
If you can solve it the easy way, why would we do it the hard way?
Why would you do the hard way? Okay, we will see. But let's do the hard way now. So area, the hard way.
We could do the easy way. It's not like we can only do the hard way, right?
Because there are cases where we cannot do the easy way.
Yeah, basically.
George, you have music playing in the background?
That's my clock here.
Okay, okay. So in this case, the half perimeter is also 6. This will be 6. 6 minus 3. 6 minus 4. 6 minus 5. It's 6. Now, what is the inradius? Okay, enter your answer in the chat. What's the inradius of this triangle? We haven't used this chat function for a while. Samuel, enter your answer in the chat. Amy and Jessica, Zisheng, Peter, Aaron, and Fred. Wow, Aaron. Okay, I'm not sure what the number is, Aaron. That's 7?
That's a 1.
That's a 1. Oh, okay, okay. Okay, that's a 1. Okay. Okay. They all get 1. Okay, Samuel, how do you get 1?
Well, I mean, basically, I just copy off from others, but like, I'm sure you need to plug the words in, like, quite honest, right? But like,
It's a way to do it. It's a way to do it.
And George, oh no, that's Spanish, right?
I don't know. Yeah.
Okay, so we
我
can
西班牙都来了。
Yes.
apply this formula. We find the area, we find the perimeter, the quotient is the radius.
Oh, 6 times.
Area over S. Okay, so for this one, because we know it's a right triangle, we can find the inradius through the area. What about the next one? If I'm going to move to 4, 5, 6, 7.
Just at 6, 7.
Let's find the inradius. When you are done, enter your answer in the chat. And then compare with others. Do you get the same answer or get different answers?
Just a question. What time is it?
What
Over-
time? George, what time is break?
No, what time is it like currently?
So now it's 8. Maybe 2 past 8.
2 past 8? What the? Mine says 2 past 9. I don't know why.
Okay. Break
Oh,
in
yeah.
10 minutes. Okay. That's correct. Okay. Jessica, how do you find this radius?
So you find half of
The half perimeter.
so you do half of 5 plus 6 plus 7,
Mhm.
which is 9, and
Mhm.
then you find the area, and then it equals the area over S.
Okay. Okay. So this will be 4, 3, 2, 6 over 6. Then the radius will be area over S, which is so this time you can check this is not a right triangle. So the easier way doesn't work at this time. We have to find the height. That's not easy. That's why we use this Heron formula, because we don't have to find the height. As long as we know the 3 sides, we can find the area directly. Now we have the area, we have the half perimeter, we can find the inradius. Okay, so this is the first application of concurrence. The 3 angle bisectors are concurrent, and it is to the inradius incircle. Why it's called inradius incircle? It's because this fact. The 3 sides are tangent to the circle at EFG. So this side is an incircular circle.
Wait, how do you do like square root division again? I forgot.
You mean here?
Yeah. Do you just only divide the 6 by 9?
No, you
Yes.
simplify.
Oh yeah, great.
Uh-huh.
I thought I lost some brain cells. It's fine.
It's called the inscribe. And we have a short name for this, the incircle. Or just incircle. Then the center of the incircle we call it the incenter of the triangle. And the radius of the incircle we will call it the inradius. So all of this, the incircle, incenter, inradius, they are the properties of the triangle. For each triangle, you can find the incenter, you can find the inradius, then you can draw the incircle. They are properties of triangles. Okay, the second application. Okay, second application is about median. Given a triangle ABC, if we pick a midpoint, the midpoint, then we connect AE. This segment is called median.
Sorry, fireworks.
Okay. Okay, a very simple fact. The median divides the triangle into equal areas. Okay, let's see how to justify this. Why? Why the two areas must be the same?
Wait, can you call those equal areas mass?
Well, that also works. So if we imagine this is a metal plate of something with uniform density, then you can replace area by mass. If we have uniform density, then you can see equal mass. So here is also area, not areas. Okay. Can you tell me why the two areas must be the same? Aaron, what do you think, Aaron? Why these two areas, ABE, ACE, it must be the same? Amy, what do you say?
Because like their base is the same since BE equals CE, and then they also have the same height. And if you divide them by 2, it's
Okay. Let's use a
Can I take the bathroom real quick?
Okay, so 1 minute, we will have a break. So because equal base equal height, this gives equal area. Okay, 5 minutes break. We'll be back at 8:18.
Okay.
Okay. Okay, 5 minutes break. Okay. Next, we will consider the medians for all three sides, not just one, but the three of them. Midpoint, midpoint, midpoint. Move a little bit. Midpoint E, midpoint F, midpoint G. Observation. Maybe it's a coincidence. These three medians are also concurrent. Three medians. Is this a coincidence or is this a law? So this is our next theorem. For any triangle ABC, the three medians.
All right, I'm back.
All right. Are concurrent. Okay. So as we have seen called before, if we assume we have the uniform density, then the median divides the triangle into equal mass. This one equal mass, and this one equal mass, and this point will be called the center of mass. Okay. Next, we will show why. We explain why they are concurrent. As I mentioned before, concurrence is a very special case. In general, they are not concurrent. Why here? So to prove this, an idea for this we will give more details later, but first, what's the idea? If we have a line segment, a second line divides this line into two pieces. We call this X and Y. This is L divides. Now if we consider another line, divide it into U and V. X and Y. Second line, let's use L. If the two ratios then the intersection points must be the same. So the first line has one intersection point. Second line is another intersection point. This intersection point divided into two segments. This intersection point divided into two segments. If the two ratios are the same, the intersection points must be the same, because this is the idea for the proof of the concurrency. Okay. So how to prove this? We will see these two medians divide this one into the same ratio. Therefore, they must be concurrent. Let me make a copy of the picture. We don't have to go back and forth. Okay, now we will start the proof of the theorem. We want to show that the three medians are concurrent. We will apply this idea. We will show that AE and BF divide CG into same ratios.
Teacher, can you take a picture of this and put it in Google Classroom?
Okay.
Like this whole.
You want me to take a picture or you will take a picture?
Can you take a picture and put it in Google Classroom?
So I'm going to post this, the document in Google Classroom.
Okay.
Divide CG into equal. Then by the previous argument, we see that the intersection points must be the same. Before the proof, these two may intersect at one point. These two may intersect at a different point. Because they have the same ratio, the intersection points must be the same. So we have concurrency. Why they are the same? Let's check. What's the ratio when CG is divided by BF? Okay, so to find this ratio, we connect FG. Next, let's recall some of the theorems we learned at the very beginning. What can we say about this segment FG? F is midpoint. G is the midpoint. What can we say about FG? Which theorem?
The midpoint theorem?
The midpoint theorem. Okay, what does it say about this? The midpoint theorem. Midpoint.
Midpoint of the other line.
By the midpoint. Okay, there are several conclusions. We use some of them. First, it must be parallel. Do you agree? Amy, it must be parallel. Okay, so that's the midpoint. The first part. G, F, G must be parallel to BC. Moreover, the midpoint theorem tells us this is half of BC. Okay, the midpoint theorem, one of the main theorems we learned at the very beginning. All right, now let's consider the two triangles. I'm going to call, okay, let's make another copy. Copy. Oh, let's keep this one. Label this A, to this B. So I will label this point H. Oh, I see. For there's a potential issue here because I want to save. I have used G. Let's see how many G. Okay, let's keep this. We call this H. Now we want to check the two triangles BCH, triangle FGH. I wanted to say these two triangles are similar. Can someone tell you why? Jessica, any idea why these two triangles are similar? We know they are parallel. Is this good enough? Amy, what do you think?
I feel like we did this before, but I either forgot or I just can't think of it.
Okay, let's check these two angles. Are they have this equal? Why? Because they are the alternate angles for the two parallel lines. These two angles have equal measure. Similarly, these two angles, you have the alternate angles for two parallel lines, equal measures. We can apply the AAA similarity theorem. These two triangles are similar. So because it's parallel. Maybe A is good enough. Similarity theorem. Okay. They are similar, so the corresponding sides have the same ratio. So GH over HC is the same as GF over BC, which is 1/2. Okay, so that's the first part. The ratio divided by BF is 1/2. Next, we will check the ratio divided by AE is also 1/2. Let me make another copy. Oops. Second part, I'm going to remove the unnecessary one. I've done it before. Now I'm going to connect So the second step, we want to find the ratio. By AE. Okay, so this time I connect EG. E is the midpoint of BC. G midpoint of AB. What can we say about this segment? Okay, Jessica. Again, we will apply the midpoint theorem. Amy, what does the midpoint theorem tell us about the segment?
It's parallel to AC.
So EG parallel to AC. And that's anything, any extra information?
The two triangles are similar.
Okay, that will be next step. So it's also half of AC, right? Okay, then similarly we have the two triangles. A. Okay, I'm going to call this point L. H. J. We'll call it K. Triangle A. C. K. Similar to triangle E. G. K. Okay, so I will skip the step. The two triangles are similar. The corresponding sides have the same ratio. So CK over GK over CK. GK over KC. This is the so GK from this triangle, CK from this triangle, corresponding to this over this. Okay, now let's see what we have done. This median divide this median to 1, 2, 1/2. This median divides the same median into 1, 2, 1/2. So these two medians divided into the same ratio. So the two intersection points must be the same. So now we conclusion. Same ratio implies the two intersection points. Okay, because H divided this into 1/2. K divided the same segment into the same ratio. So H and K must be the same. Then the three medians are concurrent. So the key point for this is to show that for a common segment, this median divides into the ratio 1/2. For the same segment, this median divides into ratio 1/2. Same ratio implies same point, so K and H are the same, but these are three medians. They intersect at the same point, they are concurrent. Okay. So this is the second application about median. The third application. Okay. So to prepare us for the third application, we have a very simple fact. Let's start with a segment. We'll pick the midpoint and draw a line perpendicular to AB through the midpoint. We will call this the perpendicular bisectors of AB. C, D. Perpendicular. Okay, because it's perpendicular and because E is the midpoint, so bisector, not just perpendicular. An important property of this perpendicular bisectors is for any point on the bisector, the distances to A and B are the same. Okay. Theorem. Any point PA equals PB. Okay, let's think about it. Why? Why is two segments must be the same? What theorem could we apply? Brad, we have two segments here. I claim they have the same length. Why? PA and PB. Samuel, Zisheng, are you still here? George?
We are always here.
Okay. Okay.
I am
Okay, Zisheng,
always.
what about you, Zisheng? What's any thought on this one? Why they must be the same? PA and PB. Amy, what do you think?
I mean, can't we like prove that they're isosceles triangles?
Why? They are, but why?
Okay. I don't know.
Okay, now let's first check this triangle PAE. Amy, what can you say about this triangle?
It's a right triangle.
Right triangle. The Pythagorean theorem, what does it tell us?
That the AE squared equals AE squared plus the PE squared equals the AP side squared.
Okay, now E is the midpoint. So I can replace AE by BE because they are the same length. Okay, Amy, what does this two give us? What do they give us? B square plus P square. We will apply the Pythagorean theorem again, we get PB squared.
Oh, sorry, I was muted.
Okay. So now we see PA equals PB because they are both positive and they have the same square. Okay, this goes both ways. What that means, if we have a perpendicular line with equal distance, then it must be a perpendicular bisector. Okay, so what does this mean? Let's do the converse.
Teacher, just a quick question.
Yes.
Like B squared, isn't B squared just like B plus AE?
BE square. Is that what George, what's the question?
Isn't B squared kind of just like B plus AE?
Why?
PA and PB is the same, and
So BE, this is the size of the right.
Is that like SAS similarity theorem? They have two sides that are the same, the two triangles, and they have one angle that's the same. So doesn't that mean AE and B is equal?
So AE and BE, they have the same size, is because E is the midpoint.
Okay.
So that's the definition of this perpendicular bisector. So E is the midpoint. So there are different ways to prove this. One way, Pythagorean theorem, or you check these two triangles are congruent. You can apply the side angle side theorem. These two triangles are different proofs. If Okay, so two directions. If we have a perpendicular bisector, then for any point on CD, they have the equal distance. The other way, if we have equal distance for a perpendicular line, then it must be a perpendicular bisector. Okay, so the third application is, let's start with the triangle. I'm going to find the midpoint, draw the perpendicular bisectors. Midpoint. A, B, C, E, F, G. Again, we observe that the three perpendicular bisectors, they appear to be concurrent. So this is our theorem. Very important theorem. For each side, we find the midpoint, draw a perpendicular line. Midpoint, draw a perpendicular line. Midpoint, draw a perpendicular line. So we have three perpendicular lines. It turns out they are also concurrent. And this has important applications. This will give us a circle that contains the three vertices of the triangle. So for comparison, this circle will because this will lead to the circumcircle. We will give a short name for this, as we have done for the incircle. Okay. So we will learn more about this next time. Why are they concurrent? How to draw the circle? This will be the center. How do we find the radius? Okay, we'll learn more about this next time. Let me check. Any questions?
No.
Okay.